Welcome to this second lecture on topology and condensed matter physics course. I'll the last lecture was an introduction to topology in general physics, and in which we have given an example of the Dirac monopole, which is seen as a singularity, and in the same spirit we have talked about Aharonov-Bohm effect, where winding, or rather going around that singularity, which is the cylinder, that's a solenoid, that gives rise to the winding, and this has to be in integer times 2 pi. We'll carry on the same discussion. However, we'll now try to shift towards the condensed matter physics and how various things that are borrowed from this topology and homotopy theory, etc., they are applied to branches of condensed matter physics, different studies of materials, and some of the experiments that are known to us to show topological invariant. So, we start with this statement that topology is a branch of mathematics. It is concerned with the special properties preserved under continuous deformation. That is, you are not allowed to do any stretching or tearing or puncturing of the object, and these properties which remain unchanged are called as a topological invariant. For example, you see that there is a coffee mug that's continuously being deformed into the shape of a donut, and the handle of the coffee mug where you hold the cup is the one that's forming the hole inside the donut. And this is it's a particular example that we are deforming an object, and it's going into another object completely different, but they are topologically equivalent. That is, one is being continuously deformed into another without puncturing or tearing or breaking that thing. Okay. Apparently, this has got nothing to do with condensed matter physics, but however, we'll show that this has very deep implications on the condensed matter physics that we study in modern times. And the whole thing was put into perspective. These studies are put into perspective since the discovery of the quantum Hall effect, that's in 1980, and has been the focus since then. And especially with this 2016 Nobel Prize that we have said earlier to Halden, Kosteles, and Thouless, this study has become much more prominent, and its applications to the condensed matter community has become in focus for quite some time now. So these topological invariants, which is just a whole here called a genus, as we'll see in the next slides. There are these similar to this in condensed matter physics. We'll be talking about topological invariants, which will be measurable or rather can be computed from the bulk properties of the material, and these are called as a winding number, the Chern number, and the Z2 invariant, and so on. Okay. There are a whole lot of classification of this, and that is what we are going to study. Okay, so it's the same picture I'm showing once again, that so that you see the snapshots of various phases of this. So if you look at the left picture, which starts with a cup, a white cup, and then it slowly gets deformed and then forms a donut, pretty much what you see on the right. So we'll have to deform a certain system, and when we say a certain system, what we actually mean is that the Hamiltonian of the system will be deformed, that is with respect to change in certain parameter. And if it can be smoothly deformed, then and gives rise to an invariant that remains unchanged through this process, then it's topological system, or the Hamiltonian denotes a topological system. And if you need to puncture it or tear it, then of course you're not getting back the same system. And In terms of the Hamiltonian, this means that some of the energy levels that are actually crossing the Fermi energy, and which is equivalent to puncturing or tearing of the object. So you have to maintain the number of levels below the Fermi energy and of course above the Fermi energy to be same. And if by virtue of this variation of the parameter, if this number, that is the number of energy levels below the Fermi energy, remains same, and then the system actually is topologically and there is a gap, then the system is topologically non-trivial. So just to give you an idea of winding number, we'll talk about them more in a detailed manner when we talk about these tight binding models, but just to give you an idea about sort of in a layman's term, you see that this is going around, and this person, there is a person at the middle who's looking at it, and this is going around the person. So if it goes around once, it's called as a winding number 1. If it does twice with respect to the center of this, the 3 vertical pictures that you see, then the winding number is 2. And similarly, if it does it in the opposite sense, that's the direction of winding is also important, and then the winding number is -2 and so on. So as soon as the winding number is non-zero, that is a particle winds a point or a singularity. So if it's a non-trivial system, then it should be accompanied by a winding number which is finite or non-zero. And if the winding number is 0, which means that it doesn't enclose the origin or the point or the person here, okay, or the singularity that we have, and that's why it will be called as a topologically trivial system. So these are some shapes from school coloring books that I've taken, and of course it's a circle, which is you all know circles and triangles, 3 sides, square, rectangle, rhombus, all these other things, pentagon, hexagon, etc., etc., octagon, there's a rhombus here, trapezium, and so on. Okay. Now, of course, they are geometrically different objects. They have no relation with one another, and a child would be easily able to distinguish between one shape to another. And however, topologically, all these are same, because we would view them as closed figures, okay, and because all of them are closed figures, all of them are topologically equivalent, okay, there is no distinction between any of them. Now that tells you that even if things are geometrically different, that is, shapes are geometrically different, topologically they may not be different, they are in fact identical or same, as is the case here. So even though the geometry and topology they are related, but of course they are not same, okay, and this is what I just wanted to emphasize from this slide. Okay, so let us come to this topological invariance, and this taken from Joel Moore's slides, and in which you see that there are 3 figures which are one of them is this one, and there is another one here and another one here, which is so there's a cylinder, and then there is a a sphere, and then there's something which is looks like 2 cones which are joined with sort of a surface area at the point of joining there. So what's different between the two is that this has a curvature, the radii of curvature or radius of curvature, which we want to sort of understand that they are different at different points. So the radii of curvature with respect to that, which is written here, so with respect to that, this is negative, this is 0, and this is positive, okay. So it's important that we understand this radii of curvature, which is basically the curvature at the, we are talking about at the equator, that is at the the middle point, like here, okay, or here. So this is what we are trying to say, that these radii of curvatures are different here. They are of course different geometric quantities, but if you are asked to calculate the integral of this radii of curvature over the entire surface area, that is usually a difficult problem. In the sense that these are very regular objects, but in fact you can just see that it is if you try to calculate the radii of curvature and then for a sphere it sort of comes out as 4 pi. But if it is a complicated object with a lot of different curvature along its surface, then it is not such an easy task to do. However, this theorem called as the Gauss-Bonnet theorem gives you an answer to this, where these chi is actually the radius of curvature and A is the surface area. So, it tells you that the radius of curvature, when it is integrated over the entire surface area of the object is say m, it gives you a constant which is 2 pi chi, which is this chi is called, it has a name called as a Poincare curvature. In any case, this is equal to 2 pi into 2 minus 2 g, and very importantly we will take this part of the equation which is very important for us, and this g is called as the genus, which counts the number of holes. And talking about the holes, we have already seen here that we are talking about really the hole that is there in the system. So, here it has a genus equal to 1. Okay. So, both the mug and the donut have one genus equal to 1, and you can clearly see that the hole in the donut, that corresponds to the genus, and where you actually hold a cup or a mug, that place where you hold is the genus, and this has one genus or rather genus equal to 1, and this is exactly that genus. Okay. So, it can be very easily verified, because for a sphere there is no genus, the genus is 0. So, if the second term is 0, the integral is equal to 4 pi, and which is a known result which you all know. Okay. So, this theorem is really connected intimately to the studies of condensed matter physics, and we will show you over a period of time, or rather as the course proceeds, that how it is connected. We will give you a preliminary idea today, but then it will be explored throughout the course, this particular theorem and its relevance to condensed matter physics. Okay. And so, this is I mean, whatever may be the shape of this object that you consider, and then if you take the radii of curvature, radius of curvature, and then integrate over the entire surface area, this gives you a constant, and this constant contains a quantity called as genus, which just counts the number of holes. So, it counts holes of the object. All right. So, this is, as I said, that will be discussed along with the real condensed matter systems. Okay. I give you examples that this has genus equal to 0, it is just an orange, there is a saucer or a plate, and then you see that these are genus equal to 1. So, as I said, that it just counts the number of, it is equal to the number of holes, this is equal to 1, and so on. And so, the genus of a particular object or a surface. Okay. This is called as a Mobius strip. Okay. You can easily make it. The only thing that is important about this Mobius strip is that it is joined in such a manner that if an ant starts crawling from here, it goes through the full ribbon, it will find itself on the other side of the ribbon. Okay. And you can see this, if you trace this path, one can understand that you come to the other surface of this ribbon, and so it has to undergo 2 such revolutions or 2 such trips it has to make in order to come back to the same surface. Okay, and so this is like that winding that we are talking about. So this really corresponds to winding the strip, or rather moving in the on the surface of the strip twice in order to come back to the same surface. Okay, this is exactly shown there. So it is sort of a cartoon in which there is a twist that is there, and if you look at the red dot or the red ball, then the red ball, after one complete revolution, or rather one complete trip on the strip, it lands up in the other side. Okay, and this is called as a Mobius strip. As I said, there should be an umlaut that is there. All right. So why am I saying this? Is there a reason that I'm saying this, or is there a relationship? This you can make it at your home in your leisure, just with a paper, scissors and glue. And the reason that we are saying this is the following. Okay, so electrons have this property. What do I mean by this? Okay, I box this statement and let me try to explain that why electrons do have this property. So what I mean is that the electronic wave function, after a rotation of 2 pi, which is a complete circle, doesn't come back to the same point. What it means is that if you start from the the trough of the wave function, then after a 2 pi rotation you go to the topmost point of the wave function, and you go one more time around it, and then you can get it at the same position. That's the trough, the next trough. Okay, so these the topmost point and the trough are not they are a different in phase. So this is called as a 4 pi rotation. As you see that the 2 pi rotation, it doesn't bring back to the same point. Ideally you would have thought every point or every function which has an exponential behavior, like for example an exponential I theta, this function comes back to the same point if you take theta to theta plus 2 pi. Okay, so these are same, but it doesn't happen for this electron, and let us see how that happens. So let us see the angular momentum of the electrons. So how do we write the angular momentum operator? Let me write a Jz for that. I'm taking the z component of the angular momentum, and this is like a minus IH cross del phi. Okay, precisely the Lz has this form, so I'm just using the total angular momentum operator. Okay, so now if you operate this Jz on a wave function, it gives you a mh cross psi. Okay, and psi actually transforms as so if you put it into the Schrodinger equation, that is, if you're trying to sort of find that this is del phi of psi, and this is equal to mh cross psi. Okay, and the solution would tell you that this psi of phi, this is equal to e to the power I m phi psi of phi. Okay, so this is like psi of phi. So this is like transforms in this particular fashion, is what I mean to say. Now electrons, by virtue of the fact that they are spin half objects, or they have the let's say the total angular momentum m is equal to half. Okay, if you are finding it difficult, you can write a Lz, only Lz. That will be in the sense that you have to, when we talk about m, then we are talking about the spin of the electron, or the this quantum number m. So this tells you that it transforms as exponential I phi by 2 psi. Okay, So that means that when you take phi to phi plus 2 pi, then psi does not return back to the same point. Now, when I say point, I actually mean that it the same configuration. Okay. So, if psi will return back because of this factor, which is exponential I phi by 2, because m is equal to half, and so phi equal to 2 pi will make it this is equal to for 2 pi this will be equal to I pi, and exponential I pi is equal to -1, and this is really related to the antisymmetric property of the wave function, that is when you swap two of them, then so this is what happens, so it picks up a -1, and the wave function really picks up a -1 when you swap two particles. Now, this is a little subtle. This happens in 3 dimensions, and if you want to do it in 2 dimensions, which many of the things or other systems that we'll study in condensed matter physics is 2-dimensional things such as graphene or 2D electron gas. This exchange is a little tricky, and there are braids that form, which I do not want to go at this point here. So, psi returns back to the same point after 2 into 2 pi, which is 4 pi, which is nothing but 720-degree rotation. Okay. And I sort of did that right after when we talk about the Mobius strips. It's equivalent to the ant, which had to go through 2 trips on the surface of the Mobius strip in order to come back to the same surface or the same point. Okay. So, this is analogous to that, and we are trying to bring in these connections of these topology and then to various systems in physics, in quantum physics, and then hence of course we will go to condensed matter physics. Okay. So, in order to understand how this connection to condensed matter physics comes, a very large contribution has been made by Michael Berry in the late 80s of the last century, or something around the end of towards the end of this the last century, through various works, and we come across a number of quantities which are named after him. And these quantities are very relevant for condensed matter systems, and particularly for understanding the relevance of topology and condensed matter physics. So, these are Berry phase, Berry connection, Berry curvature, and finally a topological invariant, which goes in the name of Chern number, or one can call it a TKN invariant. We'll talk about that. Okay. So, we'll talk about Berry phase with some details and just how a quantum mechanical system picks up a Berry phase. In fact, you can read up the parallel transport of a vector. It picks up an irreducible phase and so on. This Berry connection is analogous to what's the vector potential in electrodynamics. The Berry curvature is analogous to the magnetic field, as well as it's analogous to the the radii of curvature, or the radius of curvature. So, this is the radius of curvature. So, this radius of curvature is will behave similar to the Berry curvature. We will talk about that. And this Chern number, again let us go back to that same expression and see this. This will act as a Chern number, as you see that 2 pi is of course a constant, and for a given system, if you don't sort of puncture it or tear it, the genus will remain same, is what we have said. So, the whole thing is a constant, and this constant is the topological invariant of the system, and which is analogous to the Chern number that we will see. Okay, and it has a very nice connection with the quantum Hall effect. All right. So, let me see that how the connection comes about with all these, armed with all these quantities such as Berry phase, Berry connection, Berry curvature and Chern number. Okay. So, I just repeat what has been said, that the Gaussian curvature is analogous to the Berry curvature in condensed matter physics. The surface area, this is something very important, that what is the surface area that you talk about here? This surface area in condensed matter physics is nothing but the Brillouin zone. Okay, and you know that in solid state physics or condensed matter physics, the first Brillouin zone is the most important thing. If anything is going, or any vector, wave vector is going beyond the first Brillouin zone, it can always be brought back to the first Brillouin zone by adding or subtracting some reciprocal lattice vector. So, that is the area that we are talking about. Here we are talking about the surface area. In condensed matter physics, we will be talking about the Brillouin zone. Okay. The vector potential, as I said, is the Berry connection, analogous to the Berry connection. The genus is the topological invariant, which can be Chern number or some other invariant according to the classification of topological insulators. So, the line integral of the Berry connection is called as the Berry phase. We will sort of write that in a moment, and the surface integral of the Berry curvature is called as the Chern number, which is analogous to the Gauss-Bonnet theorem. Okay. So, we integrate the Berry curvature over the Brillouin zone, we get a topological invariant, which is let us say is a Chern number for a time reversal symmetry broken system, and for the Gaussian curvature you get sort of when you sum it over or integrate it over the entire surface area of the object, you get an invariant which contains a genus, okay, or the Poincare curvature. Okay. So, now very interestingly, this is shown a priori, but then of course we will talk about this. So, you see a donut here on the left, and then there are specks and so on, and on the right what you see is the integer quantum Hall effect graph, okay, where you plot the rho xx, which is shown in this I am not too sure whether you see it as this maroon red kind of thing, which are these ones. So, these plots are the longitudinal resistivity. So, just to tell you in a very brief a few words, you have a magnetic field and you have a 2D electron gas, okay. And what you do is that you send a current in this longitudinal direction, okay, because so there is a voltage here and you send a current, and there is a current that is moving, which means the electrons are in motion and they are subjected to a perpendicular magnetic field. So, the Lorentz force will come into picture, and this Lorentz force will make the charges, the positive and the negative charges, segregate at opposite ends of these transverse ends of these of this sample. I am not that careful about the accumulation of charges. I mean, they could be the positive could be on the lower half and the negative could be on the other upper half, but what is important is that that you can figure out from the direction of this E and the B and the motion of the charges. So, what is important is that there is a voltage that develops because of the accumulation of these charges and so on. We will tell you in details about that. So, if you calculate the voltage in the transverse direction, so there is a voltmeter, you will register a voltage because the charges have segregated, and this happens in equilibrium. And so, this was originally discovered by Edwin Hall in 1879, and which goes by the name Hall effect, and that really is this part of the plot where you see the Hall resistance, which is linear here, and of course you can measure the this magnitude resistance, that's resistance in the same direction as the flow of current, which is almost like a constant. But in those days the ability to actually access very large magnetic field was not there. So you do not in those days you did not have very large electromagnets which can produce very large fields. About 100 years later, in 1879, so this was by K. von Klitzing, who was studying the mobility of the MOSFETs. In fact, they were trying to improve the mobility of the MOSFETs, which are semiconductors with applications and so on. And he found that when he goes to very large values of fields, these magnetic field being to 15 Tesla. 15 Tesla, by the way, is a very large field. Of course, in those days, it's extremely large, and you need to have very large magnetic field facility in order to access this. He found that the Hall, which is shown on the right hand side of this plot, which are shown by these things, these plateau structures, he noticed that the Hall resistivity is quantized in unit of H over E square. Okay, so this was like H over E square, this was H over 2E square, this was H over 3E square, and so on and so forth, okay, and H over 4E square and so on. So this quantization of the Hall resistance was not known earlier, and then it was found that these plateaus are extremely robust and they are accurate up to 10 to the power minus 8 or 10 to the power minus 9, and they don't go away with increasing the magnetic field and the disorder in the system. And these are just the 2D electron gas, that is the electrons are being confined in a 2 dimension and the magnetic field is in the Z direction. So this was sort of discovery which went ahead to sort of this forms this called as the metrology, where this H over E square is approximately 25.8 kilo ohms. So that is the benchmark of resistance which is fixed from an experiment, macroscopic experiment, on really dirty systems. Dirty means there are a lot of disorder and defects in the system, and it still was able to give you these value of this resistance in terms of the microscopic parameters. H is a Planck's constant and E is the electronic charge. So H over E square is what you see here. So this helped us to benchmark the value of resistance, and H over E square is actually 25.8 kilo ohms. So if you want to know what's the value of 1 ohm, which is H over E square divided by 25.8 kilo ohms, would be the value of one resistance, 1 ohm of resistance. Okay, so this was a big discovery, and it was awarded, this Klitzing was awarded Nobel Prize after that, and this was actually the samples were obtained from 2 engineers called Dorda and Pepper. And if you want to know that why are these 2 figures that are existing on the left hand side to this experiments on an electron gas in presence of a magnetic field, then we'll say that this one hole, this is linked to this, and these have 2 holes that are linked to this H over 2E square and so on. So if you find an object with 3 holes, so that will correspond to the third plateau and so on, which means that these are the topological invariants which are called as a Chern number. So this can be written, we'll just show in a while that this can be written as the conductivity or the resistivity can be written in terms of the Chern number, it's E square over H and so on. Okay, we are talking about here we are talking about resistivity, but we can talk about conductivity, because conductivity is what is calculated using theoretically using Kubo formula. Okay, so let me sort of give you a brief overview of the Berry phase, which is what we have said, and it's just a quantum mechanical description. It's small, but it will help you understand that in certain cases the wave function picks up phases which are irreducible and they stay, and they act like an invariant to the system, and these invariants aid us in understanding the topological properties of the system. Okay. So, it's a general introduction to Berry phase. Okay, so we know that if you have this particle in a box, which is the first problem of quantum mechanics that you do, it's between 0 to L or minus L by 2 to plus L by 2. So, there is a particle there, these are infinity. So, V is equal to 0 here and V is equal to infinity at each of these things. So, the particle cannot escape, the particle is confined in the within a length 0 to L, and it's a one dimensional problem, and you solve the one dimensional time independent Schrodinger equation. It's equal to E psi, and you know that this is like the psi becomes equal to root 2 over L sine n pi x by L. So, this is solved by using the boundary condition that psi at 0 is equal to psi at L, and this is good enough to characterize the system, or rather to entirely sort of set the boundary conditions for the system. And in such a system, because of this confinement, the k is quantized as, or the wave vector is quantized as n pi over L. Okay, and let me write down psi as psi n, and I'll write down the energy as well, which is n square pi square h cross square by 2 m L square. Okay, where m is the mass of the particle of mass m. Okay, and now of course if you try to solve any wave equation just like a normal wave equation, this is different than that. This you get quantization. Okay, and this is not unknown. Even in case of an organ pipe, the frequencies are quantized in terms of nu over the fundamental frequency by 2L or 4L, depending on we have an open organ pipe or a closed organ pipe. So, the quantization is not very specific to quantum mechanics, but what is important to understand for us is that the quantization brings in a scale of h, as you see a h cross here. This h which has a value, h cross has a value some 1 point something. I'm not too sure about what comes after decimal, but that you can check. It's a 1 point something into 10 to the power minus 34 joule second. It has the dimension of the angular momentum, and this is clear from Bohr's postulate that he said that all these atoms and they exist because the electrons actually revolve around the nucleus in certain orbits, stationary orbits he called them, where the angular momentum is in terms of is quantized in terms of nh or nh cross, whatever. Okay, so that is important in the sense that h cross is the scale of quantities that we find out here. Of course, E is in terms of h cross square and so on. Okay, now we want to understand that if adiabatically, that is slowly, we change L in time, that is we make L as a function of time and slowly change it, and in addition assume that the particle is in the ground state. So, if this change is slow, that is if the width of the box or the length of the box is being increased quasi-statically or such that the equilibrium is established at all times, then the particle should be in the ground state even at time t. Okay. So, what I mean to say is that for this box, wave function, the ground state wave function has nodes at both the ends is like this. In this box also you'll have the wave function which will have nodes. Okay. So, this is 0 to L and 0 to L at a time t. So, this is L at 0. Okay. So, it is expected that this is what will happen. Now, assume that H is some function of lambda, some parameter lambda. We are not specifying what parameter that is, but these lambdas are explicit functions of time. So, H is implicitly, H depends on time through this lambda, and this lambda is a parameter that changes slowly. Okay. So, the understanding is from the problem that we have stated before is that if a system is in the nth eigenstate of H lambda 0, it will continue to be in the nth eigenstate, particular eigenstate. What I mean by nth eigenstate is a particular eigenstate in H lambda of t. Okay. If this parameter changes very slowly, which means that the system is never out of equilibrium and stays in equilibrium. Okay. So, the more important question that arises here is that what happens to the wave function. Okay. And the wave function can be written as, this is from our experience, that it picks up a phase, of course with psi at 0, we will write that in terms of the basis functions. This is minus I by h cross, and so this is like E n t prime and a dt prime and phi n of t. Okay, where of course the phi n's are the basis sets. So, you have h of t and phi n of t. This is equal to epsilon n. We are saying that the dependence is through lambda. So, this is E n of t phi n of t. Okay. So, this problem is known, that is H acting on the basis sets will give rise to the energies, of course, and this of course is true if H does not depend upon time, which we know that the phase actually comes out as exponential IET by h cross or minus IET by h cross. So, independent of time means it does not vary with time. Okay. But of course, for time dependent problems it cannot be done, that is we cannot say this, we will see how. So, in that case you have we need a little adjustment, and the adjustment is done through a coefficient which depends explicitly on time, and then exponential minus I by h cross some 0 to t, say for example, and epsilon n t prime dt prime and a phi n of t. Okay. So, I mean, as I said that this equation, let us say this equation, this ansatz would definitely be correct if h is not a function of time, that is h does not evolve with time. But suppose it does, which is the case that is going to be considered by us here, we need a little adjustment in that we add these coefficient which depends on time. So, we have written down the same thing excepting multiplying this by this quantity, so the coefficient. Okay. And of course, if you see that if you write this as 3, I mean the 3 and 1 would agree if C of t is equal to 1. All right. So, now what we do is that we put this into the Schrodinger equation, and the Schrodinger equation is we write down the time dependent Schrodinger equation here because we need to we have time dependence in h, and this is I h cross del t minus h. I am just writing both of them together, psi of t has to be equal to 0. That is the equation, and the solution of this, I am just directly writing down the solution, but you can put the psi of t what I have written in equation 3 and then do a little bit of simplification, and you would get this the equation of motion. This will be, or rather this is the equation according to which there is nothing but the Schrodinger equation written again in terms of the coefficient. So, this c dot t, this is equal to minus c of t, and you have a phi n of t, and you have a d dt. I am writing it a full derivative as in equation 4 we have written a del t, but it is same here, it is a d dt of this, and so this will be the solution of this equation, and or rather this is the Schrodinger equation. So, 4 and 5. So, putting 3 in 4 we get 5. Okay. And so, this is the equation of motion for C. The solution is obtained as, so C of t equal to C of 0 exponential minus I minus this is exponential 0 to t phi n t prime d dt prime. I am just using a dummy variable so that I can write down the limits from 0 to t phi n of t prime and dt prime. Okay. So, that is the equation, or rather that is the solution. Let us write it as 6. Let us call this as I gamma, in the sense that we will write it as C0 exponential I gamma, where gamma is equal to I. I am absorbing the I in gamma. So, this is equal to 0 to t and a phi n t prime, the simple algebra I am doing. So, d dt prime and a phi n t prime. Okay. So, this is C of t, and this is the solution of this equation in case of a time varying Hamiltonian. So, this is, let us call this as 7. Okay. And the gamma is this, and we can call this as 8, and we can call this as 7. Okay. This extra phase that comes, so gamma is called as a Berry phase, and this Berry phase is irreducible. It is an irreducible, and it is unlike the dynamical phase. Okay. The dynamical phase does not appear dynamical phase. What I mean to say is that exponential I omega t or IET by h cross and so on, or minus IET by h cross. The wave function having that kind of time dependence is not concerning, for the reason that whenever we are trying to calculate the expectation values of observables or operators, or we talk about physical observables, or we talk about probability density, these sort of do not appear because they cancel out, the phases cancel out. However, this phase will not cancel out, and we will see how. So, we ask this question that can we, in the definition of these eigenstates, can we absorb the phase, and this is what is done. So, we can probably absorb this phase also, but it will still give rise to measurable consequences. Say we explore whether basis kets can absorb this phase. Okay. And if it can be done, so let me redefine the basis kets as phi prime n, this is equal to, I take this chi of t, which is which I have defined as a Berry phase, and equal to phi n of t. Okay. So, I redefined it so that it can be absorbed. Okay. So, if you do that, then I phi n prime t d dt prime, which is there inside the phase, which is in the definition of gamma, that can be. So, let us what numbers are, so 8, and let us call this as 9. So, phi n prime t, this is equal to, I phi n of t d dt and a phi n of t. Till this point it is fine, this looked like the same, but there is a minus d chi dt because chi now depends upon time. This is new and was not there. So, let us call this as equation 10. Okay. So, this is the, even if you do this, try to modify or renormalize your basis, then also you are left with a d chi dt term, which cannot be ignored because chi is a function of time. And in order to understand that what is d chi dt or how this gives rise to measurable consequences, let us have a Hamiltonian which is like this. So, consider the time dependence of the Hamiltonian as h of t equal to t, this is same as the Hamiltonian at h equal to t equal to 0. Okay. So, the Hamiltonian is periodic with a period capital T. Okay. So, this is a particular case, but it will sort of can be done for any arbitrary dependence. So, we get this from equation. So, let us call this as 11, and so from 10 what we get is the following. We get I, and so this is over the entire cycle. So, we sort of take this phi n prime t d dt of phi n prime t. This is equal to I this and a phi n of t d dt of phi n of t. And you have there is a dt, of course, there is a dt which I forgot here, and then there is a term which is a minus chi at t equal to t minus a chi at t equal to 0. Okay. So, as I said, this is, let us define equation 12, and this is irreducible, and this is the Berry phase. So, even if the Hamiltonian is exactly same, the phase that it picks up over a full cycle from 0 to t, they are not same and they don't cancel out, and this contribution stays. And we'll see that this is exactly, we'll write down this in terms of the Berry connection, and can be the Berry connection can be related to the Berry curvature, and integrating the Berry curvature over the Brillouin zone will give rise to the Chern number. We'll stop here and carry on from here in the next lecture, and this is just to give you an idea of the Berry phase, that in a slowly varying time dependent Hamiltonian gives rise to observable consequences. It picks up an additional phase and the phase cannot be reduced, and this phase bears the testimony if it's finite, that is, if you take say an electron over a closed path and take it a 2 pi rotation, if this does not give rise to a zero observable effect on its wave function or on the observable properties or consequences that are important on its physical properties, then we say that it has non-trivial properties. Okay, the electron or the system has non-trivial properties, and this non-triviality is related to the topological properties, as we shall see. Okay, thanks for your attention.